Okay, so this is part 4 of our Unit 6 video series. Here we're going to start talking about buffers. And so a buffered solution is one that's going to resist a change in pH. That is because it has components of both weak acids and it has both a acid and its conjugate base or a base and its conjugate acid in solution. They will have that common ion, that conjugate that's there, that will allow for the absorption of a change in pH by adding a strong or acid or base. So for example, when you add an acid to a buffer, say you have something like this, in a second. If you add in HCl, it produces chloride and hydronium. Acetic acid has a weak acid with the conjugate bases here. Adding in a common ion is going to allow for the equilibrium to shift to the left to produce a solution that, while the pH has been affected, it's going to be minimal effect, as opposed to an overall dramatic effect where most of the change would be seen. So here, for example, we know that acetic acid behaves in water with a Ka of 1.7 times 10 to the minus 5. By adding in, there we go, an acid, like hydrochloric acid, it can be quickly taken off to solution and leaves you with a more neutral solution overall. So the addition of acid is going to cause only a minimal effect of your pH here. Same thing, like I show this video in class a lot. The idea here is that by adding in base, so here we have a strong base on this side, a weak base on this side. By adding in a small amount of strong acid, you're going to see a dramatic influence on the left and only a slight influence on the right. And that's because the one on the right is considered a buffer. It's got a weak base and its conjugate salt that will readily adjust your pH. Let's see if I can. There we go. So it went from something like 9.2 to 3.74 on the left, only down by a 0.02 change. Over here, it's a very small difference. And so that's the impact that a buffer will have, is that the pH is only going to be affected slightly in a buffered solution. So when we're talking about buffered solutions, you want to take the original solution. You're going to do a simple subtraction of what reacted. Was it an acid that you added? You subtract that out, and then you recalculate your new pH. The idea is that the final pH of the buffer should be very close to the original. Now, the way that we do this is we have a ratio of either an acid with its conjugate base or a base with its conjugate acid. The idea being that ratio is what saves the overall pH of solution. Now, these problems can usually be done with a simple equation. This is on your equation sheet. The pH of a buffered solution is equal to the pKa plus log of the A minus over HA. Now, this is any acid that can ionize to give H plus and A minus. It's just the unprotonated form over the protonated or acidic form. So what is the pH of a buffer solution that is 0.45 acetic acid and 0.85 sodium acetate? Well, we have our HA of 0.45. We have our A minus, that acetate of 0.85. And so we can go back and plug this into this equation. So our pH is equal to the pKa plus the log of A minus over our HA. And that's because this is how it would be written in our K equation anyway. Now, P just means negative log. So negative log of that 1.8 times 10 to the minus 5 plus the log of 0.85 over 0.45. And we can really just plug it in just like that. Negative log 1.8, oops, to the negative 5 plus the log of 0.85 divided by 0.45. And you should get something right around a 5.02 overall. The idea, again, guys, is that you have a buffer. A buffered solution is going to have hopefully close to equal amounts of acid and conjugate base. It means if you add in strong acid, it's going to produce a little bit more protonated acid, but the relative ratio of these is constant. Add in hydroxide, it reacts with some of the acid, leaves you with some of the unprotonated form, and you get still a very similar ratio. So the pH is only going to be adjusted slightly. Now, to have a really good base, you need large concentrations of your weak acid and its conjugate. You need to also, really, these are the two things. You want large concentration of your weak acid and its conjugate, and you want relatively equal amounts of your weak acid and its conjugate. Now, to find the pH, it's going to all come down to that ratio between your weak acid and its conjugate base in that equation. If you add in strong acid or strong base, you're going to have to do a small subtraction before you plug this stuff in. So you're still going to need an ice chart. So optimal buffering is when you have equal weak acid and its conjugate, and you have a strong acid, a strong concentration that you are going to have. The higher the concentration, the more buffering you get. Now, when you choose a buffer, the pKa of that weak acid has to be close to the pH you want your solution to be at. So, for example, if you want your pH to be something like 5, you want to choose a K value where your pKa is going to be close to 5 as well. The buffer is going to be pH plus or minus 1 of the pKa value. And so you really need to choose based off that pKa. Now, when you are looking at titration curves, you can look at, in general, strong acid and a strong base. You have acid. Let's do this. We'll do pH mils base. You have a strong acid, strong base. Start off with a low pH. You add in some base, and you get a dramatic change. If you have sodium hydroxide, now you have a high pH, you're adding in a strong acid, you get a dramatic decrease. Your equivalence point here is going to be right at a pH of 7 where you have equal hydroxide, equal hydrogen. That is not always the case with the weak acids and base systems, guys. So here we have a strong acid with a strong base. Completely ionizes. Strong base added in. And they continually form water until they've completely reacted. and then they're done. The equivalence point is going to be right at 7 for those systems. If you have a weak acid with a strong base, pH, milliliters NaOH added. You start off at a low pH, you get less dramatic influence, and your pH is going to be a little bit above 7 at your equivalence point. For a weak acid, excuse me, let's do a weak base, adding in a strong acid. Same thing, you're going to get a dramatic increase only once you've completely reacted that. So here the equivalence point, the pH is going to be less than 7, because you have a weak base, which means some of it is still going to be in that base form. You're not going to have completely all of it there to react. So here, consider a solution made by mixing 0.1 moles of HCN with 0.04 moles of NaOH in a 1 liter aqueous solution. Now initially, guys, we have two things we're talking about. HCN and sodium hydroxide. Sodium hydroxide is a strong base, so it is going to completely dissociate. This is a weak acid, so this is the dominant form here. This is the dominant form of this reaction. And we can really talk about the major species. And it's all based off those K values. A strong base completely ionizes. A weak acid would rather be molecular than ionized. So we know that sodium hydroxide is not a major species because it wants to dissociate. H plus and Cn are not because it is a weak acid. They tend to stay together instead. And so we can really look at all of the possible reactions. The problem is, guys, we know, for example, that this is 1 times 10 to the minus 14. This was something to the negative 10, 6.2. Yes. Which means we can really look at which of these are going to be dominant. We know this has got the smallest K value, so it really shouldn't be the one that contributes the most. This one has got a stronger K value, but it's still relatively weak. And so we really need to consider how the acid and the base are going to react to give us something that's left over. So we're going to look at how these guys are going to react. So in order to do that, we're going to consider how the base reacts with that weak acid. We're going to do a little bit of an ice chart, and then we can find our pH. And we're going to do it here with acetic acid. We're just going to pause for 1 minute. Okay, so when we're considering a reaction like this, we have, our acetic acid, which in water will ionize to give H3O plus and acetate. Now here we also have base, and anytime you have base, you have to consider what is going to happen when you add a base. And you're going to have this base and this acid react. You have 0.2 moles of this. You add in 0.03 moles of a strong base, it's going to react to essentially give you O3, a starting amount of 0.17. You also know that if this much reacts here, it's going to form some of your conjugate. And that is really hard for students to see sometimes. And so remember, when we're talking about this, as far as the weak acid goes, H3O2, this is the side that dominates. As far as our base goes, any strong base you add is going to completely ionize, so that this is the side that dominates. And because we're in water, water always H2O self-ionizes. This side is going to dominate. We know that this is not a dominant species because it's a strong base and those completely ionize. We know that these are not major species because it is a weak acid and it does not completely ionize. Tighten, stop. So in general, we know this guy cannot happen because a weak conjugate is not going to react. We're not going to reform our hydroxide. So we only have the reaction of water self-ionizing, a weak acid ionizing, and our weak acid reacting with a strong base. These are the three reactions we need to consider. Now, we know that the K here is 1 times 10 to the minus 14. It's not going to be the one that controls our pH. Technically, we then have these two reactions that we have to consider. Before we can plug in to this second equation, we have to consider how much is going to react with our base in this third equation. So technically we started off with this amount of acid. We add in some amount of strong base, and we're going to have an overall starting material that is slightly different than what we might have originally thought. Now because of that, we can then go into plugging it into our original K equation for just the weak acid, which is here. By setting up our ice chart and knowing that we can discount our X because of the value of this K, we can solve to find our H plus concentration or our X value. And then we can go one step further to finding the pH here. You should get a pH of 3.99. If you don't, it's because you did not count this 0.03 molar conjugate base. Now, calculate the pH of a solution where you have 100 mils of 0.1 molar acetic acid and a Ka value of 1.8 times 10 to the minus 5. All right, tighten. Let me just pause for a second. Okay. So here we have a solution that is acetic acid, HC2H3O2, in water, which will completely ionize, or not, which will ionize somewhat to give the hydronium ion and the acetate ion. We have the concentration of this. So we know that initially we have 0.1 molar, 0 and 0, minus X, plus X, plus X. When we look at this value, we have to consider the fact that 0.1 is a little bit larger than this 1.8 times 10 to the minus 5. And so we can really discount this x and just say that this is 0.1, this is x, and this is x. When we do that, we get our k value is equal to 1.8 times 10 to the minus 5, which is equal to x times 0.1, or 1.8 times 10 to the minus 6 is equal to x squared. And if we take the square root of both sides, you should get something like x is equal to 1.34 times 10 to the minus 3. Now this is just the concentration of our H+. To find the pH, we need to take the negative log of that concentration. And you should get something like 2.8 or 2.87. Now it gets a little different when we start titrating that with a strong base. Here we have a similar problem to the one we had a few minutes ago, where we had acetic acid in water, which will ionize to give hydronium and acetate. But remember, if we add in a strong base, it is going to take away some of our acid, C2H3O2 plus NaOH. It's going to give acetate. We'll just leave off this and leave it as an ion. Now, if we have initially 0.1 molar times 100 mils gives us 0.01 moles. And initially we have 0.05 liters times 0.1 molar, or 0.005 moles. We're essentially going to subtract this. So we know that we're really going to have 0.005 moles of this initially, and we're going to have 0.005 moles of this initially. This is what happens when we add in that strong base. And so initially down here for our acetic acid solution, we have 0.005 moles, 0.005 moles, something minus x, and plus x. And while it is still true that we can probably discount this x, we really should go back to molarity first. And so I just want to put that back in molarity. Instead of saying 0.005 moles minus x, we're going to divide that by the 0.15 liters to give us 3.33 times 10 to the minus 2 minus x, and 3.33 times 10 to the minus 2 plus x. Now it becomes a little bit more evident that we can, in fact, discount this x. And our x value is going to be determined from our k expression. So here we have k is equal to 1.8 times 10 to the minus 5, which is equal to x times 3.33 times 10 to the minus 2 over 3.33 times 10 to the minus 2. So x is equal to 1.8 times 10 to the minus 5. That is our H plus, or our hydronium ion concentration. And so we can take the negative log of our H plus, or 1.8 times 10 to the minus 5, to find our pH. And it should be something like 4.7, I think. Negative 5, 4.74. And so make sure you are subtracting. When you are titrating, you have to subtract from the a weak acid with a strong base, subtract from the acid, add that same amount into the conjugate base before you plug into your ice chart. And then just like we were talking earlier, your equivalence point is going to look different depending on what you're titrating. As far as buffers go, buffers are going to be able to titrate really, really well, plus or minus 1 unit from that pKa. When we do that, it really allows us to target a reaction by using a specific buffer. So if we wanted to have something maintained at a pH of 6, we would look for an acid or a weak acid with a pKa of something to the -6. It allows us to really target our reactions, and so that we can monitor when we can resist those pH changes. Now, in lab, you mark the titration with a change in color from an indicator. That's going to be your end point. It's usually a drop or two beyond your equivalence point, but hopefully they'll be really close. And so I think you guys did this in 111 where you used phenolphthalein. Sometimes in 112 or organic you'll use something like methyl orange, but you can actually choose an indicator that will change color at the pH near your equivalence point, which is really helpful. I don't expect you guys to memorize these. If you go into organic, sometimes you have to. Some places require you to know certain ones. But for us, all I want you to know is you can target a reaction by using a specific indicator that will change colors around your equivalence point. And that is it for this unit.